Okay, welcome students. So today we'll discuss the effect of wavelength, frequency and speed during diffraction. In this topic, we will discuss the effect on wavelength, frequency and speed of light as it passes from one medium to another. Fine. Now, consider a source of light. This source of light is in your medium 1 and the light is traveling from medium 1 to medium 2, and in medium 2 you have a observer. Fine. Now we have studied that light can travel in a ray or it can travel as a wavefront. AB is your wavefront. Now this light takes some time to travel from your source to the observer. That time is known as your time period. Fine. Now let us say, suppose your wavefront AB takes time t to travel. Let us say it takes 10 seconds to cover this distance. So after every 10 seconds you will receive a new wavefront. In that case you are getting light after every 10 seconds. Now let us consider another case. Again consider the source of light which is in one medium. There is a observer in your second medium. Now this time your wavefront AB is traveling little bit faster. It is covering this distance in lesser time. Let us say small t. So let us say in this case you are receiving a new wavefront after every 1 second. So what happens is that in this case you are receiving light more frequently as compared to your first case where you are receiving your light less frequency. So from here we have understood a new term, frequency, which is denoted by your symbol mu, and frequency equals to 1 by t, as we have already studied in your class 11. Fine. So frequency of the light, it totally depends upon the source of the light. If the source of the light produces light after very long duration, in that case your frequency will be low. You will receive lights at very low frequency. But when your source of light produces light at very less time, in that case your frequency will be high. That means you will receive light very frequently. Fine. So from there we can understand that frequency is inversely proportional to your time. The higher the time, the lesser will be your frequency. The lesser the time, the higher will be your frequency. Fine. The other point is that the frequency is the characteristic of the source. Not all of the source have the same frequency. Fine. Only the source of the same color will have the same frequency. Rest they will all have a different frequency. So I can say that frequency is a characteristic of the source. Fine. Okay. Now moving on from medium 1 to medium 2. Okay. So medium 1 is a different medium. It is a rare medium of refractive index mu1. Medium 2 is your denser medium which has a refractive index mu2. Fine. Now we know refractive index mu. Now we know refractive index of the medium is the ratio of speed of light in vacuum to the speed of light in medium. Okay, so speed of light in vacuum is a constant. It doesn't changes, whereas speed of light in a medium is a variable. So it changes. So I can say for a different medium, the light will have a different speed. Fine. So in this case, your medium 1 will have a different speed of light and medium 2 will have a different speed of light. Fine. Now as the speed of light V1 and V2 are different in the two media, the medium 1 will have the velocity or speed V1, the medium 2 will have the speed V2. The wavelengths lambda 1 and lambda 2 will also be different. Why? Because of this relation. Your velocity or your speed V equals to lambda mu. So for medium 1, it will have the velocity 1 and wavelength. So for medium 1, the velocity will be V1 and the wavelength will be 1. But since it has the same source, the frequency will not change. It will be a constant. Fine. So I can simply write mu. For medium 2, the velocity will be V2 and the wavelength will be lambda 2. Fine. Okay, this relation we have already studied in your class 11. So from now, I have just said that your refractive index is inversely proportional to the speed of light in the medium, that is V. So from here I can write mu 2. So from here I can write mu 2 inversely proportional to V2, mu 1 inversely proportional to V1, or in terms of fraction, mu 2 by mu 1 equals to V1 by V2. Fine. Now V1 equals to frequency mu into lambda 1, frequency mu into lambda 1, and V2 equals to frequency mu into lambda 2, frequency mu into lambda 2. Now your frequency, they are same, so I can cancel frequency, so I have lambda 1 by lambda 2. Hence the wavelength in medium is directly proportional to the wave speed V. Fine. And inversely proportional to the refractive index. What does this mean? If you have a higher wavelength in medium 1, the velocity will also be high. Fine. But inversely proportional, what does this mean? If you have a higher refractive index, what does it mean? Lambda 2 is inversely proportional, means the wavelength will be small, so as your velocity. For a higher refractive index medium, your velocity will be small and your wavelength will also be small. Fine. Okay. Now based on this concept, we will move further. The refractive index of a medium with respect to the vacuum is mu equals to speed of light in vacuum divided by speed of light in medium. Fine, which is C by V. Now we know for most of the mediums, the refractive index mu is greater than 1. Fine. This one is greater than 1. So from here I can also say that the velocity of light in vacuum is greater than the velocity of light in medium. Thus, what does this mean is that the light travels in a free space, that is in a rare medium, faster as compared to the light speed in any other medium. The speed of light in an optically rarer medium. Optically rarer medium means free medium, like this one, which is air, is greater than in the optically denser medium. Optically denser medium is like the second medium. It can be any medium like your glass or your air. Fine. So if you have any confusion in this one, you can ask me. I will re-explain it to you again. Fine. Okay. So now we'll discuss behavior of the light, behavior of the light as it propagates from a prism or from the lens or from the mirror. Or in this topic we will discuss the action of the prism, a convex lens and a concave mirror when a plane wavefront is incident on each of them. Fine. Now this figure shows a plane wavefront AB, which is your incident wavefront. It is moving towards your prism. Now let us consider the first part, the top part of the wavefront, which is A. Now can you see A is traveling from the lesser part of the prism. If it travels from a lesser part of the prism means it will spend less time in the prism. If it spend less time in the prism, what does it means? Its velocity will be slowed, but it will be slowed very least as compared to the down wavefront C. In this down wavefront or the down part of the wavefront C, what happens? It propagates through the prism again, but in this case it is propagating through a greater section of the prism. So what happens? It is spending more time in the prism. If it spends more time in the prism, that means the velocity of the light will be slowed down more as compared to your top part A. Therefore what happens? Your wavefront bends or it gets tilted in this direction. Fine. Now consider the behavior of a convex lens. This is your convex lens. Again in this case what happens? Your central part B, the wavefront which is flowing through the central part B, what happens? It travels or it spends more time in this convex lens as compared to the ending part, your A and C. So what does this means? The velocity in this B part will be slowed down more as compared to your A and C. Hence in that case you will get a wavefront which will be focused towards F and it will be curved in the shape like this case. Fine. Now let's move on. Now the behavior of a concave mirror. Again you have the wavefront AB. Now in this wavefront AB, consider 3 points A, B and C. Now what happens in this case of A, B and C? As you can again see, who travels more distance in all of the three cases? It is B. So if it travels more distance, that means the time will be more as compared to A and C. That means after reflection, who will be going first? A and C. B will be following them after some time. So in that case what happens? Your light is bending in such a manner. Fine. Okay. So based on the topics we have just studied, I have given you a question. You can do this question as your homework, but I will find out the first two part. Okay, so let us read the question. Monochromatic light of wavelength 600 nanometer is incident from a air on a glass surface. What are the wavelength, frequency and speed of the refracted light? The refractive index of a glass prism is 1.5. Fine. Now what happens? You have a two mediums, medium 1 and medium 2. Your medium 1, in your medium 1 there is a source of light. Fine. And your medium 1 is a optically rarer medium, which is air, whereas your medium 2 is a optically denser medium, which is a glass. Fine. So a light is propagating from medium 1 to your medium 2. Let us say this is your wavefront, which is moving from your medium 1 to medium 2. Fine. Now during the refraction, as I have already said, will the frequency of this light will change? No, the frequency of the light will not change, because the frequency is a characteristics of this source. Fine. Now as we have know that velocity, or I'll say the speed of light, c equals to frequency mu into lambda. Fine. From here I can find out the frequency. Frequency mu equals to c by lambda. Fine. C by lambda. Now the velocity of light in air is a constant value. C is a constant value, which is 3 times 10 to the power 8 meter per second. Now in the question they have given the wavelength of the light, which is how much? 600 nanometer. Nanometer means 10 to the power minus 9. Fine. So 600 into 10 to the power minus 9. Okay, so we can solve this one. 8 minus 9 will go up here, so what will become? 8 and minus 9 goes up, it will become plus 10 to the power 8 into 10 to the power 9, it will become 10 to the power 17. Fine. Now 3 divided by 600, so 3, this will be 200. Fine. 200, or I can also write this one as 2 times of 10 to the power 2, and here is 10 to the power 17. So this 2 and 17 will get cancelled. I will have 10 to the power 15. So I have 10 to the power 15 divided by 2. Fine. Or I can also say 10 into 10 to the power 14. Fine. So now 2 divide 10 is 5. So I have 5 times 10 to the power 14. So how much is the frequency of light? 5 times 10 to the power 14, and the SI unit for frequency is hertz. Now next we will find out the speed of the refracted light. For speed of the refracted light, you can use this formula, mu equals to c by v. C is in vacuum, V is in medium, so we have to find out so for speed of light in medium we can use this formula, mu equals to c by v. C is the speed of light in vacuum, V is the speed of light in medium. Fine. So I can write velocity or speed of light in your medium, which is glass, equals to c divided by your refractive index. What is the speed of light in vacuum? 3 times 10 to the power 8. And in the question they have given the refractive index of the glass, how much? 1.5. So I've written 1.5. Now 1.5, 2s are 3. So 2 times 10 to the power 8. So the speed of the refracted light is 2 times 10 to the power 8. Now you have to find out the wavelength. To find out the wavelength of the glass, you can use this relation. Okay, lambda equals to velocity of light, where in glass divided by the frequency mu. Fine, this will give us the wavelength. Okay, so do this question as a homework and submit it to me on WhatsApp. Fine. Now moving to the next topic, principle of we will discuss principle of superposition of waves. Now in this topic we will state and explain the principle of superposition of waves. Now what does this principle states? It states when a wave or the number of waves traveling through a medium superpose on each other, the resultant displacement at any point at a given instant is equal to the vector sum of the displacement due to the individual waves at that point. Okay, so what does this mean? When the number of waves travel through a medium simultaneously, okay, now what does this mean? Okay, so consider your consider your first wave. Okay, so consider your first wave, this yellow one. Fine, this is your wave. This wave, let us say this is propagating in this direction. This axis denotes your time, this axis denotes your displacement. Fine, now this wave has a displacement how much? Y1. Fine, now consider another wave. Which is also propagating in the same direction, which is in this direction. Again, this axis represents your time, this axis represents your displacement, and it has a displacement, let us say y2. Fine. So what does the principle says? If two waves are traveling through a medium and they superpose on each other, what does this means? Superpose. Let us say so when two waves are traveling through a medium, they superpose each other. What does the superpose mean? Suppose consider this one was your yellow wave, this one is your second wave, which is your red wave. These two waves are superposing each other, that, or in layman terms we can say one wave is placed on top of the other. So in that case, what happens? The resultant wave, let us say we will denote it using the black one. The resultant wave at any point at a given instant will be equal to the sum of the displacement due to the individual waves. Fine. What does this means? In this case, the displacement is how much? Y1. Let us say it is 1 unit. In this case, the displacement is how much? Y2. Let us consider this one also as y2 waves. So when these two waves superpose each other, the resultant of this two waves, let us say this black one, okay, this black one will have a displacement which is the vector sum of the two waves. Now what do you mean by this one? The red wave had a displacement 1 unit, the yellow wave had a displacement 1 unit. So the resultant wave, which is your black wave, will has a displacement 1 plus 1, how much? 2 unit. So this distance will be 2 unit. So as in this case, this distance will be how much? 2 unit. And in this case also the distance will be 2 unit. Fine. This is how the two waves superpose each other. Now to get a clear picture, let us take a look at this figure. Now in this picture, can you see this point? This is 1 unit, this is 1 unit. When these two waves superpose each other, they give rise to a resultant wave. This third wave is your resultant wave, and this resultant wave will have a displacement how much? 1 unit and another 1 unit, 2 unit. 1 unit plus 1 unit gives you 2 unit. So this one represents your resultant wave. Fine. Consider in this case. In this case, the displacement is minus 1 unit. Here the displacement again is minus 1 unit. So what happens at this point? Minus 1, again minus 1 will give you how much? Minus 2 unit. So the resultant wave has the displacement how much? Minus 2 unit. Or I can say when these two waves are mixed, this is how you'll get your resultant wave. Fine. Here also 1 unit, 1 unit, the resultant 2 unit. Fine. Now the important one is your third case. Look here carefully. Now in this case, the displacement is how much? Plus 1 unit. and in this case the displacement at this point is how much? Minus 1 unit. Now if you take the vector sum, plus 1 and minus 1 will be 0. Okay, let me divide this one into intervals. Okay, now consider at individual points. Let us say at this point, this one is 1 unit, this one is minus 1. Plus 1 and minus 1 will be 0. So your resultant will have a displacement 0. Fine, at this point it is 0, at this point it is 0. So the resultant wave amplitude 0. Again at this point the amplitude is minus 1 unit. In this point plus 1 unit. Resultant amplitude minus 1 plus 1, 0. At this point 0, 0, 0. Resultant wave 0. Again at this point 1, minus 1, you have 0. So your resultant will be a simple wave. That means what happens when such kind of a wave superimpose. Let us say this is your red wave and this is your yellow wave. Now if these two waves superpose each other, what happens? The resultant wave or these two waves will cancel each other, so therefore there will be a no wave. Fine. So I have discussed with you the 3 cases of the superposition. So if you have any confusion, you can ask and I will re-explain it to you again. So that's it for today's class. Thank you.